So first of all, I have a gift for Francesco. 1.9 pounds of message passing, but I can't find Francesco. But I'll track him down. You guys will help. Okay, so I'd like to talk about the IoT revolution, and I will actually come to the strong types because I know that there are a few programmers in the audience here. Okay, but first let's talk about the Internet of Things. And it's everything, or as a friend of mine says, it's the next 100 billion devices. Real soon now, right? So what happens in revolutions is each time we get, oh yes, you've arrived, just in time for your present. 1.9 pounds of message passing.
I have this.
Oh, you have this, okay. You have this. In that case, now you've got two, even more message passing.
I have to sign this.
That's right, yes. I've signed it. Yeah, okay. So it's everything, right? So let me just keep track of the time here. How long am I supposed to talk again?
45 minutes.
45 minutes. Okay, so therefore 20, 25. Okay. So, we have a mess on our hands when it comes to IoT. Because we have all these manufacturers and their solipsis. So you get your refrigerator from manufacturer X, and it says, don't you know your data is valuable? It goes to our data center. You get your TV from manufacturer Y, it says, don't you know your data is valuable? It goes to our data center. And X and Y are two Korean companies, I won't actually name them, that hate each other. Their data centers are never going to talk to each other, right? So the citizen sits there and says, woo, we're screwed. Okay. So the idea is to make these things which we call islets, okay, for integrating the information locally. And this has several very important things. One is that we'd actually, for things like the car here, there's our car, doesn't have time to go back to the data center, okay, in order to break in time to keep from killing the kid. There's just not time to do it, right? And there are other things as well, namely these 100 billion devices, if they were all directly connected to the data centers, would just completely overwhelm the poor data centers. And besides, the data centers are too busy making money off advertising, they don't want to bother with this. Okay. So the idea is to create these things called islets, and there's a problem that we live in a world in which you have to recoup the investment for things. Means you have to make money. So these things have to be profitable. So the idea for making them profitable is to do a better job than the other guys who are firing these targeted advertisements at it, to do a better job, okay? And then you say to yourself, how can this be good? Well, there actually is a reasonable business here connecting merchants with consumers, right? There really is. The consumers in their nature have this excess income that they need to spend, and the merchants need to stay in business. So there is a process that ought to be mutually agreeable by which you can do this. So the idea is to have to do it the way they do it now through these brokerages, like Google and Facebook, right, are gigantic, and the other guys are just gigantic brokerages. And so that's the idea here that is being pushed. So there's a fly in the ointment, something called Burr-Feinstein. And it hasn't passed yet. They're waiting for the next terrorist attack, don't you know? Says covered entities must provide unencrypted information and technical assistance to the government pursuant to a court order. And a covered entity is just about anybody you can conceive of. And the court order can be just about anything you can conceive of. So the contractors have gone to work and designed a gigantic concurrent system which conceivably could be implemented in Erlang, but you might think about whether you want to sign up for this one or not. It's called Nyborg. Nyborg stands for Nothing is Beyond Our Reach. Gigantic concurrent system based on message passing, right? It's a technology. It's as Oppenheimer said, you know, they came to him, the physicists came to him and said, you know, we found out that Germany doesn't have the bomb, right? Let's internationalize this thing. And Oppenheimer said, well, look, the Japanese don't want to surrender, and it's only 20 kilotons. We dropped that much on Dresden, right? This is just another weapon. But unfortunately, Stanislaw Ulam had an idea. We got together with Teller, and they invented something 1,000 times more powerful than what we dropped on Nagasaki and Hiroshima. At that point, Oppie said, oops, this could kill us all, but it was too late. So Teller was quite happy to be known as the father of the H-bomb. Nobody wants to own up to Nyborg. So what goes on with Nyborg? Okay, they're keys. You have to have crypto's keys, okay? So you generate a public key, private key pair slice in a Faraday cage by special hardware in multiple independent U.S. government command posts in such a way that the private key slice never leaves the Faraday cage in which it was created, okay? Software never sees these private keys. If they're going to do this, they say, it's not going to be like Clipper. You may know about the Clipper chip. If not, Google it in Wikipedia. This time, we're going to, quote, do it right, end quote. Okay. Now, also, encryption and decryption is performed in the Faraday cage, invisibly to all software of its command post. The public keys are distributed to authorized manufacturers for installation in IoT devices. Each IoT device, all 100 billion of them, get a different public key. So you say, nobody's going to use this. Well, welcome to the Nyborg Internet. On the Nyborg Internet, in order to connect with the public Internet, a device must present a certificate from the manufacturer that if it receives a packet that decrypts using its public key, then it immediately uses the packet as a bootloader to take over the device with a virtual machine without disrupting its ongoing activity. So the device is taken over, invisible to you, while you're talking on the phone. Okay. Now you say, well, what about if I take my phone to France? They say, well, we have a deal for you. Okay. As Roger said, each company spies on its own citizens, and then we trade. So if you go to France, then they come back to the NSA, or the FBI, whoever's got this thing, right, and say, okay, we suspect this guy. We won't let him on our internet unless you let us spy on him too. What about it? Okay. And then the security of this thing. One of the interesting aspects of this is the security risk is mostly assumed by the manufacturer of IoT devices, that they cannot be taken over except as described as above. And if necessary, they know they're going to have bugs in this thing. A device can be taken over repeatedly. Okay, so what's going to be the cost of this thing? Well, they like the system so much that they think that they want the nuclear command and control system to use it, and that thereby provides another source of funding. It also means that this system will never be made public, because, don't you know, it controls the nuclear command and control system. And there is another expense here, namely, if all the countries do this, then we have to audit against Chinese and Russian backdoors in our phones. That'll make it slightly more expensive, but this is not going to be cheap. So there's a concurrent system for you. And there's an article about this that I've written, actually published on something called the Social Science Research Network. You just Google me and that, and you can get the whole article. So now that I've made your morning, let's go back to the Internet of Things, right? So one of the interesting about the Internet of Things is at any point, it can be totally disconnected. Your car can be out of connection with other stuff as you drive through various areas. You might drop your cell phone in the swimming pool, right? Your Wi-Fi comes on and goes off. Your refrigerator getting repaired. So that means that the islet has to operate distributed across all these intermittently connected devices. Just a small matter of software, somebody says. Okay. And also, because the clock cycle hasn't been going up for a long time, the only way to get performance is to have lots of cores. And that means massive concurrency. Just the kind of thing you guys are interested in. So, long time ago, different coast, back there on the right coast, there were these things called actors that were invented a long time ago. Now, actors, like quantum mechanics, have been a work in progress. This means that, Schrodinger didn't really understand quantum mechanics when he first wrote down his equation, right? There was a lot of work that was taken that had to take place after that equation, before quantum mechanics. And there was the matrix mechanics, there was Feynman diagrams, there was quantum electrodynamics, there was quantum chromodynamics. So it was not initially conceived, in its full blown glory in 1973. But it had a simple idea from the start, It's all conceptually based on message passing. And so the way it's modeled, and this is modeling, when an actor receives a message, it can concurrently send messages to actors that it has, create new actors, and designate how to process the next message it receives. So fundamentally down here, there's something that's very simple. And, but now life begins to become more interesting. It's message passing using types. Messages are the unit of communication, but you can only send a message to a recipient using its type. Because it might be a mechanical arm or some other piece of hardware, right? And each one of these pieces of hardware, if you ever had to deal with this thing, it likes to have its addresses in a certain form, right? And has to follow a certain protocol. So if you've got some type, refrigerator from manufacturer X, that will be a separate type, and it has to talk to its hardware using a certain type and using other types for other kinds of messages. So, what does this mean? It means the types are heavy lifters. Types just aren't, little strings like integer or float or a count, right, that you compare string-wise. They're full-fledged actors in their own right. This is strong typing amplified. So the types have to do equality, they have to do typing, subtyping, they have to do the messaging, they have to do the encryption, and they have to do the marshalling to get the messages from one IoT device to another IoT device. So these things are heavy lifters. So this is the interface for type of a particular type brilliantly called A type. For example, A type might be integer or it might be float. Well, this is pretty abstract. Let's do something simple. Let's be brave and have a program, but a really small program. So here is a small program. It says I get in two floats and I ask if they are equal to each other. So that's what equal question mark is. We don't use equal because it's not the mathematical equality, right? This is the thing that returns a Boolean. How do you do that? Well, what's really going on behind the scenes is we ask float, we send this message equivalent and gives it n and m, and let this actor called float, which you thought was just a string, this actor called float, let them decide whether or not they're equivalent. So that's an example how we're beefing up the types to make them full-fledged actors in their own right. So let's do something a little bit more. Now we're doing the deep dive. So those of you who don't like chicken scratching can now tune out for the next 5 minutes while we dive deeper. Promise you we'll be back soon. Okay, what do we have here? We have an actor, of course, but this is an expression actor, something which is, do I have a pointer? I don't. Okay, I'll try to avoid falling off the stage this time, which is an expression of type, which is what happened when I keynoted here last time, expression of type Boolean. And little half-moon guys here, they're meta parentheses. Okay. In this particular dialect, parentheses are used only for grouping and for nothing else. So therefore, these are meta parentheses, and it says it's an expression. It says this is between the half moons is an expression asking whether this thing is equal to that thing, and these two things are expressions. So this thing in half moon, where did it come from? It came from here. This is an expression. So what we're doing is we're giving the semantics for that expression using message passing. So how do you do that? Well, you've got an expression to the left-hand side of the equal question mark, an expression to the right-hand side of the equal question mark. They must both be expressions of some type. So we're going to implement expression of Boolean using when an eval message comes in with an environment E, we return a Boolean, and the way we do that is we ask the type whether the values of these two expressions are equal or not. So it's like baseball. The umpire sits behind home plate. When the person comes sliding into the plate, whatever the umpire calls, that's it, right? If that says out, he's out. Says safe, he's safe, okay? That's the deal. The types rule. Okay. So, what else can we say here? There's some funniness going on here about distinguishing between programming languages, and what we just saw was a programming language, particular one, funny chicken scratching stuff, don't you know? We're distinguishing between programming languages and models of computation. Why bother with a model of computation? Well, a model of computation enables you to reason about whole classes of systems, right? So if I came up with something that you couldn't implement in Erlang, right, that wouldn't be saying as much as, oh, there's a whole class of things that can't be implemented. Maybe Erlang could be tweaked in some way so it could do it. So, what can't some things not do? And this we know from models of computation. Here is a simple account, and it's the ordinary checking account, and it's got messages coming in from all around the world. We've got get balance messages, and we've got deposit messages, and we've got the withdraw messages. And if you get a get balance message, then you return my balance, local variable that I've got. If I get a deposit message, then I update my balance with the amount. If I get a withdraw message, then we have a conditional test here. The question is whether amount is greater than my balance or not. If it's not greater, then we decrement the balance. Otherwise, we return it, throw an exception. Okay. This is something we can prove something about. The lambda calculus can't do this. This means that pure functional programming means all you fans out there can't do this. Logic programming is not so popular in this community, but pure logic programs can't do it either. Don't tell Kowalski. Okay, so that's one of the things you can do with a model of computation that you can't do with a programming language. And it gets even more interesting. Even if you have whole systems right and you kludge around, right, which you can do with the lambda calculus, and you could put a little piece of global state up at the top, right, and just switch, click, 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 just like in the original object-oriented programming with Christian Nygaard and Ole Dahl. Basically, Christian Nygaard was a young guy. He's a great big Norwegian, very friendly guy. I enjoyed many a late evening at the wee hours drinking Linné Aquavit with Kristen in the dorms of Aarhus University. He was a terrific guy. So he went there and they got themselves a reactor and they were afraid the thing was going to blow up Oslo. So his job was to simulate it. And he got busy and they invented Simula 1 and then he got together with Christian Nygaard. They did Simula 67, and that was the birth of object-oriented programming properly. But it was a simulation system. It had a global state. The clock would go tick, 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 tick. Now, he did it in a modular way so that each one of the little things that was being simulated only knew how to simulate itself and interact with the other things it was directly connected to. So it was a modular form of simulation, but it was lockstep simulation. So if you're a believer in functional programming, for which we use the lambda calculus as our bogeyman, or pure logic programs, you have the problem that if you have a big organization, most of the action is lateral communication within the organization with the various pieces updating their own local states asynchronously. So there's no global clock that goes thump, thump, thump for the Department of Defense. And as each thump comes in. So you see, the reason the lambda calculus and pure logic programs are thousands of times slower is they have to go back to the root each time. They have to actually do the global clock thing. Go back to the root, okay, bringing all the local state back to the root, and then for the next clock cycle, distribute it all the way down to these guys, and then gather it all the way back up again to the root, because in the lambda calculus and in pure logic programming, the director of network assessment cannot update their local state asynchronously. So this is why we have a model of computation. It's so that we can prove things like that. And this is why we have quantum mechanics. So when the woo-woos, when the quantum mechanics says you can't do something, and the woo-woos say, yes, I can, then the physicist says, here's quantum mechanics, go and learn it. Okay. So, the idea is to have these islets for two reasons. Well, there are two aspects of doing the islets. One is we use the actor model computation to implement them, and we use the islets to protect the citizen-sensitive information against Nyborg. The idea is to declare for each citizen that their personal IoT in their islet is protected against self-incrimination. The Fifth Amendment in the United States. And basically, your insulin pump is part of you. Okay? Same thing for your pacemaker. And in the course of the next 8 years or so, these little devices that we all have in our pockets are going to be replaced by something else. And you say, what could possibly replace these 6 billion devices in only 8 years? That would be pretty amazing. Won't completely take over in 8 years. But it turns out the computer eyeglasses, never mind certain big manufacturer down south who didn't have such great luck with the first go, are going to replace these things using holographic eyewear. Hard to believe, isn't it? But it's going to happen. So those eyeglasses also will be protected against self-incrimination. So Big Brother can't literally say, I see what you see. That's what we're up against. What was it somebody famous said? You want it darker? Okay, so we're going to have a meeting on this. We can talk about it today down at Stanford. And you can look it up yourself if you've got one of these favorite little devices handy, right? It's http logic-collaboration.org. And we've been here before. This guy, J.C.R. Licklider, who I actually had the pleasure to know at MIT when I was there, a really great guy. Lick, we call him Lick, L-I-C-K. That was his name. He just went by Licklider. I mean, if you have a first name JCR, you might go to, as Lick also. So here's the deal. In 1962, decades before personal computers and internet became household words, the revolution that gave rise to both of them was set in motion from a small, nondescript office in the depths of the Pentagon. In an age when computers still meant big, ominous mainframe, mysteriously processing punch cards, what are they? The occupant of that office, an MIT psychologist named J.C.R. Licklider, had somehow seen a future in which computers would become an exciting new medium of expression, a joyful expression to creativity and a gateway to a vast online world of information. Lick had that vision. And now he was determined to use the Pentagon's money to make it all happen, and he did. As director of IPTO, he funded the MIT Artificial Intelligence Laboratory, the Stanford Artificial Intelligence Laboratory, Newell and Simon at Carnegie, and Doug Engelbart at SRI. He started the funding for all of them and made the revolution happen. Probably the most important computer scientist that you may not have heard of before. So Lick was pretty fantastic. And that gave birth, because see, that was the thing. That was when the computer came out of the big glass room, right, and went onto everybody's desk, and now into everybody's pocket. And now, with the Internet of Things, it goes into everything. Has an IP address, and if Nyborg comes to pass, a backdoor to boot. That's the question of the hour. What are the computer scientists going to do with this one? So, we're going to set up a table at lunch today. Please come join me. We'll get a big table in back and talk about all this. So I think I've left a little bit of time for questions.
Right. Does anybody have any questions?
From the back.
Very noble goal. How do you avoid, you're just trying to be a man in the middle attack. So they've got decent crypto, the devices are going to call home, and mostly it'll be done. So I don't see how you break that connectivity. I agree it needs to be broken, but it might be a legal problem, not a technology problem.
Well, there actually is an Academy of the Academy of Sciences, the U.S. Academy of Sciences, which actually has convened a panel that is actually studying the issue of the backdoors. And I've been talking to them, And I've been urging them to issue, they have a 1-year mandate, and they were thinking of waiting a year to issue their report. It says, no, no, no. You need to issue a report now. So I'd urge you to go to the National Academy and the director of this, the administrative director of the study is a great person. I've talked to them and urge them to issue a report sooner rather than later, because we are still in the early stages of this, right? This is when the invention was made. It was made in Germany, lots of it. They discovered how to split the bomb in Germany. Split the atom in Germany. Of course, the bomb was made here. Funny thing about that. But this is still the early stages. This is the point at which Nyborg has been invented. It has not been implemented. It will not be trivial to implement. They're important policy things. They need legislation. They have to pass Burr-Feinstein in order to make it legal. So it's a very complicated socio-political, technological issue that the computer scientists now face. This is the moment the physicists faced, and look what we got. The question is, can the computer scientists do any better? Question?
When did you learn to laugh like Vincent Price? No, that's a different question, sorry. When did you learn to laugh like Vincent Price, I said?
Ah, okay. I don't know. I've been practicing.
No, it's based on the talk. So you said that lambda calculus and logic programming can't do what the actual model can do. And I saw that basically you use a typing system which seemed to be dynamic rather than data compilation type, it seemed, right?
Well, all this stuff gets incredibly complicated. In order to prove something can't be done, you have to have a model of computation. And then you say in the model of computation, okay, you have a way of explaining in that model of computation the lambda calculus and pure logic programs. And then you prove the theorem that in that model of computation, they can't do it.
This is just Gödel's theorem, right?
No, that's another thing, which if you look in that book that I just gave Francesco, Gödel actually got his theorem, it was technically wrong. In other words, the proposition I'm unprovable is not actually a proposition of mathematics, because it fails for interesting reasons having to do with this talk, namely it doesn't type check. The proposition I'm unprovable does not type check. That doesn't mean that incompleteness, it's not woo-woo land, it doesn't mean that incompleteness is wrong. Instead, there's a different proposition that is true but unprovable, a different proposition about the integers. The proposition about the integers that is true but unprovable is that the proofs of the theory of the natural numbers are computationally enumerable. That is true, but it cannot be proved within that theory. So that is the true but unprovable proposition. And if you want to learn more about that, come to the event next week at Stanford.
Right, but that's what Gödel said, right? If you take a set of axioms, there are things outside of that set of axioms.
That's right. It is true that there are true but unprovable propositions, but he got the wrong one. Sorry about that, Gödel. Right. So, and we knew that there must exist true but unprovable propositions because of the work of Church in 1936, where Church proved that it is computationally undecidable to decide whether or not a proposition is a theorem or not, whether it can be proved. That is computationally undecidable. And because it's computationally undecidable, it also there must be an inferentially undecidable proposition. Because, hold on to your hat, otherwise we could decide whether any proposition is provable or unprovable by simply enumerating all the theories and to see whether its truth or its falsity is proved. And that would be a decision procedure. There can be no decision procedure, algorithmic decision procedure, so there must exist an undecidable proposition inferentially. Dumbfounded. Question?
I love Lick. Lick's cool. Lick had a wonderful paper, Man-Computer Symbiosis.
That's
Do you
right.
see us getting closer with the IoT?
Yes, in the following way. Namely, we will have intelligent applications, but we will not have, for now, artificial intelligence. Which means the name of the game now is collaborating with humans to make more intelligent systems. The computers cannot do it by themselves. In that respect, Lick was absolutely correct. What he, a psychologist, called symbiosis, we now call collaboration. Effective, intelligent applications must have intense collaboration with humans or be ineffective. What that means in practice is that we will have computer-assisted driving for our cars for a long time, at least a decade, and we will not have computer-only driven cars because we can't do it. And we had a long history in AI where we claimed we were going to do certain things by date X, and then date X would come and we were very, very far from doing it. History is unfortunately repeating itself. So that's a good point about Lick and collaboration. Collaboration with humans is the name of the game. And that's what this event in Stanford is all about. Good question.
Anyone else?